Okay, everybody, we're going to kind of pick up where we left off in our discussion of sensation and perception and get to the area where we're talking about theory. We're going to see how this works to get us through the end of this week, and hopefully I'll see you guys next week in class. I want to say a little bit about theoretical approaches to sensation and perception and tie in a little bit to the ideas that we have about the way that the brain works and processes perceptual information. When we look at different kinds of theories of recognition, how it is that we see things in the world and relate it to our experience, there are a couple of different things that we can look at. One of the first ideas that theorists looked at was the idea that we have specific cells in the brain that are tuned to very, very particular kinds of stimuli. And we call this the grandmother cell or the Gnostic cell theory. And the idea here is that there is a cell or a set of cells that particularly are responsive to one thing like grandmother. Or we can call it a Gnostic cell, a knowledge cell, a cell that encodes a very particular kind of knowledge. And if we look at the evidence in favor of this theory, what we see is that there are some cells that do seem to work like this in a very limited kind of basis. So if you look here, this is a representation of the firing rate of a particular cluster of neurons in response to a very particular stimulus. And what you can see here is that this particular cluster of neurons is optimally firing when it's being presented with a hand that is facing in its direction. Now, if you flip the hand to the other side, you see that there's a reduction in the firing pattern. When you look at a glove, or a glove that's turned to its side, or a mitten, or other kinds of things that are somewhat perceptually similar, are related to being human, you see the further off you go, the less firing you're getting. You're getting optimal firing with this one particular stimulus presented in this one particular way. And there is some evidence that there are some cells that we process this way, but for the most part, that's not really what we see going on in the way that we are encoding recognition information in the brain. And it kind of makes sense that this is not the most cognitively economical way to do it. If we have every single thing in the universe somehow encoded, then that gives us some problems. Number one, it doesn't give us a very flexible system that allows for learning. Secondly, it's easier to wipe out information if it's all encoded in one particular cell. So it's not good cognitive economy, it's not good flexible learning, and although there are some things that we do seem to encode that way, like human hands, which are things that are very salient to us, possibly as a threat, or possibly because we use our hands, we do see this kind of response specificity for certain kinds of things, but on a very, very limited basis. Instead, what we tend to really focus on are theories of recognition that involves features, and these are a lot more flexible in terms of the way that they work. Generally, feature theories work according to an ensemble hypothesis, and the idea here is that we can recognize complex things based on specific kind of features. In this example of features, we're basically making the argument that we can recognize these individuals based on a limited number of neurons. We can look at Bill and recognize Bill. If we can compare Bill in terms of like the specificity code, a neuron for Bill, a neuron for Samantha, a neuron for Roger, and we've seen how that's really not the best way for us to recognize them. Instead, we can recognize them based on features that they share in common. And we're not really saying what these features are in this particular example, but Bill is high on neuron 1, medium on neuron 2 or feature 2, and low on feature 3. Samantha is highest on feature 2, medium on 3, and low on 1. And you can see with the same 3 neurons, just sort of coding at different levels, we can recognize 5 different people with 3 neurons, whereas it would take 5 neurons, and you can sort of extrapolate that out with the number of people that you know. So in general, in terms of cognitive economy and flexibility, we tend to focus on these feature kinds of theories. And feature theories work in a lot of different ways. One of the earliest theories was a theory called pandemonium that was put forward by a cognitive psychologist named Selfridge. And Selfridge modeled this idea based on a representation of hell and demons. It's a really very strange kind of choice of images. But what's really important for us is not so much that, but the way the system is set up in terms of its feature detectors. It is both hierarchical and parallel, meaning that we are looking for features that are operative at particular kinds of levels, and all of this operation is really happening at the same time. Right? So we have different levels. We have images. So we have cognitive processes that are trying to detect particular kinds of images. In this case, we're looking at letters. So image detectors that are looking for things like A's. Feature detectors, he calls them demons, but we're going to call them detectors because they're neurons. We're looking for feature detectors that are looking for particular parts of a letter, like the slant of an A. We have cognitive detectors that are giving us some information about what the A means. It is a letter that we can use to form words. And basically there's this overarching kind of perceptual process where we have the cognitive detectors, the feature detectors, and the image detectors all working at once, and the decision detector is making an ultimate decision about, given the relative input at all these levels, what is it that I'm looking at? Is it an A? Is it an R? Is it a 4? Is it a B? Right, based on the relative activation of what's happening at the image level, the feature level, and the cognitive level. Now, one thing that's really important about feature detector models is that we have to be able to have something that does not get bogged down in detail. So here we have an example of a sentence, glory may be fleeting, but obscurity is forever. We've got to have a model that's able to recognize that G's may take different forms, L's may take different forms. Perceptually speaking, we have to have multiple levels going, because if we're just really focused on one level, a G, especially a G that's going to be configured in a particular way, we're not going to get very far if we have variability in the way people produce G's. So this gives you a sense of why we need to have different levels. Having like a feature-based level is not going to be enough because people make G's in different ways. A G can have different kind of features. So in order to compensate and allow us to respond to all the different possible G's that may be out there in the universe, we have to be able to look at G's that are round, G's that are curvy, G's that are more angular. And we get around this problem by looking at G's at different levels, kind of a conceptual level of G, a meaning-based level of G, and a perceptual-based level of G. And we can put all these things together and sort of realizing what it is that we're looking at and constructing meaning. Another kind of way of looking at the way that we can put things together in order to recognize them is through a theory called Geon theory that's put forward by Biederman. And the idea here comes from evidence that we have specific response properties of cells in the brain that respond to complex kinds of shapes, or what Biederman calls geons. And these shapes we can combine together in infinitely many ways to create these geometrical kinds of solids. So it's a way of looking at the structure of the world in terms of features, but more complex kind of features than the way that we're used to talking about them. So we're talking about more than angles or lines. We're talking about these geometric kinds of primitives. And we can find cells that are optimally responsive in association cortex that conform to these kinds of shapes. So here, for example, we have two geons. One is a sort of cylinder that makes up like the base of this coffee cup or pail, however it is you want to look at what the shape is. And then you have another one that is the handle or the pail. And what geon theory allows us to do is to take advantage of the evidence that we do have cells that respond to these complex kinds of shapes, and that what we can do is construct an understanding of the world based on putting these geons together in infinitely many kinds of spatial arrangements. So these basic shapes we can use to create a coffee cup or a pail or infinitely many things. And depending on the theory, the version of the theory that you look at, you're going to have 20, 30, some odd examples of these volumetric primitives that have been identified. And these just give you some examples of how we can use these geons to put things together. We can create an old-style telephone from geons 2, 3, and 5, a suitcase from 2 and 5, a coffee cup from 5 and 3, a pail from 5 and 3, a lamp from 4 and 3. And so the idea is that this is one way that we can sort of assemble a basic understanding of shapes in the world. It's a little more complicated than just looking at a whole bunch of different features based on the known response properties of objects in the visual system. Right? We're putting these things together. It's kind of an aid, a shortcut in creating this sort of complex structure of the kinds of things that we're going to encounter in the world. And again, the main evidence is that we have particular clusters of cells that are optimally responding to these complex kinds of geometric shapes. Another more cognitive kind of theory that doesn't rely so much on the known properties of neurons in the visual system is that we create prototypes. We create a representation of things, and we compare individual objects that we encounter in the world with the idealized representation of what things are that we expect to encounter. So for example, here we've got two different things. Both of these are chairs. Both of these are equally chairs, but which one of these is a more idealized representation of a chair? And most of us, I think, would agree that it's the one that's at the top, the one that has 4 legs, a back, right? Even though it's really not more of a chair than the other thing. We seem to extract these kinds of prototypes or ideas about what a perfect or more normal, everyday, expected kind of chair might be. And that one of the things that we do in order to recognize things is to compare things that we encounter with these idealized representations. And it turns out that it's a lot easier to detect, or a lot faster. We can detect both of these kinds of chairs. If we look at them and are asked, what are these, we will identify them as chairs pretty quickly. But you do identify the more idealized representation a little bit faster, right, relative to things that are not more idealized representation, showing that we really do seem to be using some kind of templates in our process of recognizing things in the world. Now, there are some theories that suggest that maybe we really don't maybe we have these templates, and maybe sometimes they can be useful, but on some level we're doing something very fundamentally different when it comes to recognizing objects. It doesn't necessarily depend on any kind of stored representation at all. And the idea behind this direct perception or ecological theory put forward by the Gibsons is that we are directly acquiring information about objects from the environment. And when we look at something, we might be looking at it in terms of its basic features, but on some level we're just looking at it in terms of what can we do with it, and what information are we getting from observing, what it is that we're seeing. So what is a chair? From a point of view of a representation, a chair has legs, it has a back, it has features. From a direct perception or ecological point of view, what do we really need to know about a chair? A chair is something that affords sitting, that allows us to sit in it. So we're just looking for something that we can sit on. And in that view, complex representations really aren't necessary. Then instead of really looking for features, we're looking for what are called affordances, things that we can do, a more functional kind of view of objects. So if we kind of put this all together, the view that we have is a complex one that depends on the response properties of cells in the cortex, the geons, some kind of cognitive work whereby we are creating prototypes, and some kind of just very basic process by which we're just simply looking at our functional relationship to what it is that we're seeing and figuring out how we can act on that on an everyday kind of basis. Now, another thing that's really important with recognizing things is our own relationship to the object, our sense of how we are related to the things that are around us. And one thing that tends to kind of drive our ability to recognize things is perceptual constancy. The fact that we can move from higher level light conditions to lower level light conditions, and things don't change in terms of our perspective, even though in some level they really are changing rather dramatically. So if I'm in the front of a room showing you something and I turn the lights off, I'm bathed in a very different kind of illumination that really is fundamentally changing what it is that we're looking at. And even though that's the case, you don't really perceive it that way. You're not going to perceive the color of my shirt changing when I turn the lights on and off. Even on some level, some very real level, it is changing. And this illustrates something that's very important about our perceptual system, that we want to preserve some kind of order. It would be very confusing, if the world seemed to be a very different place every time the light level of illumination changed. The sun came out from behind a cloud and suddenly the world looks like a very different place. Right? But what this idea of perceptual constancy really reminds us of is the fact that there is a very powerful illusion in a way that's really running cognition, an illusion of sameness, an illusion of continuity. Now, when we recognize objects, there's a kind of continuity that's created based on our relationship with the object that is both viewer-centered and object-centered. And depending on what we're kind of focused on in terms of our recognition, we can see elements of the way that we're looking at an object in relation to other objects and in relation to ourselves. When we look at viewer-centered recognition, one thing that we can see is that our ability to recognize things in some way is going to be the result of how we interact with it. So if we look at all these different perspectives of a horse, which ones look the most horse-like to you? And probably it's going to be the first few are going to be the most horse-like, and the last few are going to be the least horse-like, although of course they're all horses, they're all equally horses. But why do we have an easier time recognizing horses from particular vantage points? And it's just simply the way that we're used to seeing them. It's just basically our experience guides what we tend to expect to see in the world. Now, one major thing that's really important for us to think about is a distinction between what we can call bottom-up processing and top-down processing. Bottom-up processing is information that we're getting from the environment. It's feature-based. So when we're looking at things in the world, it's going to be what angles are we seeing? What basic features are we seeing? Geons fit in this category. Line orientations fit in this category. Color fits in this category. And top-down has to do with the expectations that we have based on our experience. And every perceptual act that we have is a combination of bottom-up processes that are feature-based and top-down processes that involve some kind of expectations, our experience, what we want to see based on our familiarity, the context in which we are typically observing something, the expectations that we have. Right, so just to give you a few examples of we've already spent a lot of time talking about feature-based stuff. So features are basically what is the basic information that we're using, to get anything at all. Lines, geons, color. What are we seeing? Top-down is really more how we're interpreting that. So if we look at this top-down image, we might recognize Lincoln in it, even though there are really no features that tell us for sure this is Lincoln. It just sort of activates an image of Lincoln that we are familiar with. What is this? And given the context, it can really be different things. We might see it as an A. We might see it as an H in a certain context. And given things that are surrounding it, we can influence what it is that we're likely to see. So the exact same thing can be seen as an A or an H depending on what's around it, even though it has the exact same featural-based properties. So I can see it as A, I can see it as H, I can read it as A, the cat, the right side of the chair. It can be different kinds of things depending on what the context around it might support. If I show you something like this and kind of flash it at you, we're not in class, so I'm not going to do it the way that I normally would do it. But people who are flashed this kind of scene tend to not notice that there's a sofa that's floating in the air, because we simply do not expect to see that happening. Right? Context plays a role. We expect to see things in certain configurations, in certain places, at certain times, depending on the way that we've been conditioned by our environment. We notice things when they're presented in a more coherent way. So this is an image of a kitchen that's a lot easier to see like this. It's a lot harder to see individual components like this, even though it's really the same picture, because we're obscuring that coherency. Another example of top-down influences is what we call the word superiority effect. People recognize letters better in the context of a word or words like the man versus non-words like omnet, even though it's the same letter. We're going to recognize the letter better in a context that's familiar to us. The foibles that we have with proofreading are another example of the way that top-down influences work. Proofreading your own work can be very, very hard. Why? Because you know what's there. You wrote it. You're going to be impervious to picking up errors, violations of things that go against what you meant to write in your own work. So we're very bad at proofreading because we're such good at top-down processing. We know what's supposed to be there, so it's hard for us to detect the errors that we might make. Now, shifting gears a little bit to kind of talk about perception in a different way, I wanted to say a few things about what we call lower order visual problems. So we've been talking about higher order problems of interpretation, higher order issues in terms of how we organize and perceive things based on experience. Lower order visual problems are just looking at what's going on with the mechanism of the visual system. And there's some interesting things that we can kind of spend some time talking about that I want you to review that give us some sense about the way that the vision is put together. When we see in color, there are different kinds of things that can influence that process and interfere with it. Achromatopsia is cortical color blindness that's caused by damage to area V4 in the brain. Most of the kind of color blindness that we experience is at the level of the pigment, in the eye itself. But it can happen at the brain, and it would happen here in the cortex area V4. We also see some basic vision problems where sometimes individuals have difficulty detecting motion. And we call this akinetopsia, or motion blindness. It is caused by bilateral lesions of the temporoparietal cortex. So we can lose color, we can lose motion, we can also lose depth. There are a lot of cues to depth, so it's kind of hard to wipe depth out completely. One of the big things that we have is binocular disparity. If you lose that slight difference that we get between the image of two eyes, people can lose depth perception. But it's hard to get rid of depth. We can interfere with it. But one thing that we cannot do is interfere with form blindness. Or interfere with form perception to the point, rather, that you get form blindness. There are so many different cues to form that it's almost impossible, it really is quite impossible actually, to wipe it out completely. So if someone says, I can't see color, of course there are reasons why they might not be able to do that. They might not be able to see motion. They might not be able to see depth very well. But form blindness, which I suppose would just be like disembodied color, there's really no way for that to happen because we just have so many different cues for form. Someone who really is experiencing or claim to be experiencing some kind of visual experience that is divorced from form, it's just really hard to imagine how that really could be the case. Now, higher order visual problems we've spent some time talking about already. So blind sight, we have damage to the primary visual cortex, or people will not be able to report seeing things. Remember, we're going to have the 10% of those axons that are going to superior colliculus, that are going to retain some ability to see where in space objects are located. And we also have agnosia. And apperceptive agnosia is linked to right hemisphere parietal lesions and is associated with very specific kind of deficits that are interesting. Apperceptive agnosics have a really hard time shape matching. So if you give them something on the left and ask them to match the shape on the right, they have a really hard time seeing the shape and being able to match it up. So you can see here this patient is having a really hard time doing that kind of task. There are other kinds of agnosia. So here's copying apperceptive agnosia. You're having a hard time like just taking the object and copying it. But a different thing that we can see is an unusual views test that shows that this is a real perception problem with people with this kind of agnosia. The eye, we can present the eye in a conventional view, unconventional views, and the subject has to say whether the object is the same or different, and they really have a hard time with this. Associative agnosia is a kind of agnosia where they may be really good at copying, but they just can't like put it all together. They can copy a key perfectly, but they still can't tell you it's a key. Copy a pig, but not be able to tell you it's a pig versus a dog or some other animal. Also, functional impairment, where you have to decide which of the two objects is the same function, is a real problem in associative agnosia. So here they're making a really confusing function with appearance. Have a really hard time figuring out that the umbrella is the umbrella like folded up. They're going to get confused by the fact that the folded umbrella is going to look like the cane. So here's a functional problem for associative agnosia. It's different from what we're seeing with the apperceptive agnosia. Another kind of higher order visual problem is prosopagnosia. Here's an example from Oliver Sacks' famous book, The Man Who Mistook His Wife for a Hat. can read because my language is going out. So there's some very specific kinds of visual problems that we can see. Human faces is a very specific area, the fusiform face area that is activated when we're looking at human faces. That is damaged with prosopagnosia. Now we can recognize people in other modalities. We can recognize things and people from.
Okay, folks, I'm going to pick up where we left off in our
sound.
lecture.
And sound works the same way.
And hopefully, I'm going to see you guys next week.
We compute sound based on.
Today, we're going to finish up talking about theories of recognition and perceptual functions, both higher and lower.
With animals and
first, I want
humans,
to talk about the idea of how it is that we recognize things.
we can be agnostic for audition as well.
Neural processes might underlie that kind of recognition. The first thing that I want to talk about is the idea of grandmother or Gnostic cells. And the idea here is that we have a very specific set of cells that are responsive to highly specific stimulus. The notion that we can have a cell or set of cells that optimally responds to grandmother or to one particular person or to one particular object. We also call this Gnostic cell theory or knowledge cell theory. And there is some support, very limited support, for this kind of theory, neurologically speaking. It's supported by single cell recordings from inferior temporal cortex that are optimally responsive to things like hands. So what you see here is that a particular set of neurons is optimally responsive to a hand, but not only to a hand, but a hand presented in a particular orientation, palm out towards you. If you flip the palm, if you look at a glove on the side, or a mitten or an oven mitt, or a comb that approximates the general shape of a hand, you're going to get varying degradations of response. But optimal response is going to be to a particular stimulus and to a particular stimulus presented in a certain way. And what this may tell us is that hands are things that are very important for us to pay attention to be aware of threats, right? But for the most part, we don't really see this kind of organization in the visual system. It's not very good from a cognitively economical point of view to have particular sets of cells that are dedicated to highly specific stimuli in this way. It's also not good if you have brain damage and you lose a set of cells, you're going to lose knowledge. All right, so just from a basic point of view of cognitive economy, it doesn't make sense to have an organization like this, and we really don't see a whole lot of organization along Gnostic cell lines. Instead, what we see is recognition that is the result of an analysis of features across an ensemble kind of pattern of neural firing. This kind of feature-based theory argues that we have a series of neurons that are activated to help us recognize things, and this is a collective pattern of activation where we can recognize things in terms of particular features. If we're talking about individuals, hair color, face shape, whatever the particular features are, the idea is that there's an ensemble of neurons that work together to allow for that recognition. And this kind of account helps us to recognize novel or atypical objects. And we know that cells in the inferior temporal cortex prefer certain things, but they will respond to perceptually similar things. Right, so here in this particular example, we can have a neural ensemble that can predict recognition of these 5 individuals with 3 different neurons. So Bill is high on neuron 1, medium on 2, low on 3. Hillary at the very end is high on 1 and 3 and low on 2. This just gives us a lot more functional flexibility in our ability to recognize things. One particular aspect or example of theory of recognition that I want to talk about is Selfridge's classic pandemonium model. And the way this works is in a hierarchical and a parallel way. And Selfridge, for some reason, was really caught up in the ideas of hell and demons, and Milton's idea of the general structure of the underworld. But we don't need to get caught up too much in that. Instead of demons, what we're really talking about are neurons, specifically feature detector neurons. And these work in a hierarchical way in that they're all focused on different levels of analysis, and they are parallel in the sense that they're all working together. So what we see here is several different levels. We have neurons that are looking for things at the level of images. If we're talking about a letter, that's going to be the image of the letter A. We're also looking at things basically in terms of their individual features. So an A has features like certain line orientations, and the feature neurons are looking for those. Then we have the cognitive level, the cognitive neurons, which are looking for meaning. And so we have one that actually means A, the phoneme A, that's going to be important for us in language. We've got different ones that have similar qualities, like R and 4 are similar in terms of their perceptual features, but they're different in terms of their meaning and in terms of their images. And then ultimately at the top we have a decision neuron that's pulling all this together to decide what it is that we're actually looking at. So in order to recognize an A, we're at the same time processing that stimulus at multiple different levels. At the level of the image feature, at the image neuron rather, the feature neuron, the cognitive neuron, the decision-making neuron is kind of pulling it all together for us. Now, one really important feature of these kinds of models is that it helps us to ignore irrelevant differences in shape. We can learn, we can adapt to new stimuli. Right, so here, for example, we have the same sentence printed in a lot of different ways, but we all recognize it as meaning the same thing and having the same letters. That would not be possible if we didn't have representation at all these different levels that we could rely on. One problem that we kind of have in looking at these features is how many feature detectors do we actually have? It's another issue of economy. We tend to recognize objects pretty quickly. We don't need to go through a set of features, and why is that? How can we simplify with the smallest number of features our system so that we can recognize as quickly, as accurately as possible? And one very promising approach is the GEON approach from Biederman. And what this approach involves is a recognition based on volumetric primitives that correspond to the response properties of specific neural cells in association cortex. Alright, so these cells are responding not just to simple shapes or line orientations, they're responding to these very complex kinds of geometric figures. And here are a couple of examples. You've got these two shapes. One is kind of a canister kind of shape, one is a handle kind of shape. And what we're actually perceiving as the basic feature are these two objects. And we can put them together in lots of different ways spatially to arrange them as pails or as coffee cups or whatever it is that we're looking at. Now, these kind of structural theories assume that the objects are, that we're looking at these objects and the relationships among them. And these complex objects can be decomposed into simple objects based on a finite number of basic shapes like cylinders, cones, and so on. I think the most recent theory of Biederman's is a 36 GEON model. I think your book has a different number, 24 maybe. It really, it doesn't, we're still trying to figure out exactly how many of these basic shapes they might be. But beyond that, one problem is that there's only a very subtle difference geonically between something like a Shetland pony and a St. Bernard. Right? So we need something else really to kind of help guide us in terms of object recognition than just looking at these shapes. something else has to guide the way that we put them together and that we represent them. And this is where we come into prototype theory. And we can think of prototypes as idealized representations of things. So if we think of a dog, what's an ideal dog? Probably a collie. It would be more ideal, and something less like a miniature chihuahua. Or a chair, which of these two things would we think of first as a chair? It's likely to be the one with the back and the legs, even though that this sort of rounded chair is perfectly chair-like. It just doesn't fit as well our idealized representation of what a chair should be. And we have idealized representations for lots of things. What's an ideal bird? It's probably a canary or a robin rather than a penguin or an ostrich, even though they're all equally bird-like. So we use these kinds of prototypes in order to kind of help classify what things are. Right, but we can also use a much more basic kind of information in order to recognize things that doesn't depend on storage in any way. And the Gibsons are psychologists, Jackie and Eleanor Gibson, or Jackie and Henry Gibson rather, are two psychologists who have really pushed the idea of what's called direct perception or ecological theory. And the idea here is that perception is much simpler than than constructing all these kinds of templates. They reject the idea that you actually need to construct a mental representation of object and events. Instead, the perceiver doesn't need to really work that hard because we've got enough information in the world so that we don't have to construct representations and draw inferences from them. We can instead directly acquire perception from the environment. The retinal image itself contains highly organized information that requires very little interpretation on our part. Right? If you kind of look at this from a very functional kind of perspective, chairs are not necessarily defined by their features in so much as they're defined by what they do. What makes something a good chair? It's something good to sit in. Right? That's basically the Gibson's points, that we don't need features. We can just look at the affordances of the things that we can do with the objects that surround us in our environment. Now, there are plenty of things in the retinal image itself that don't change, and the Gibsons point those out as things that really kind of help us in recognition. One of them is the perceptual constancy that we kind of perceive with objects, even in changing circumstances. If I were in front of you and walking around the room, there would be different levels of light illumination falling on my face and my shirt, but you're not going to perceive me as a different person given that I'm being illuminated in a different way from one second to the next. We can look at what's constant about the relative value of luminosity in my clothing, or parts of my clothing to each other, and use that as a way of showing that it's still me. Right, so again, there's a lot that's really just present in what we're looking at, and the Gibsons are arguing that we don't necessarily have to come up with really complex representations, to recognize things and keep, a sense of visual order. Now, there are other kinds of things that help us to maintain our sense of what things are and how they are related to other things in the visual environment. We can look, for example, at the relationship of the individual parts of an object relative to the viewer-centered scene. So here's a single object, an image of a horse that's seen from 12 different perspectives. Are they all equally horse-like? Yes. Do they all equally look like horses in terms of our ability to recognize them as horses? No. The scenes that are more common, looking at the horse from the front and the side, are slightly more quickly recognized as horses in timed tests than situations where you're looking at the horse from above, even though it's still a horse. Why is that? Well, it's just kind of what we're used to in terms of our context. Our view, our understanding of the world is mediated by our relationship to it. So we're used to seeing horses from a very particular angle, and that affects the way that we're able to recognize them. Now, another big issue within perception that I want to talk about is bottom-up versus top-down processing. And we've already spent a lot of time talking about the bottom-up part. Bottom-up is information in the environment. So what is the bottom-up information that we have? It's basically going to be the features. It's basically going to be the geons. It's the raw data in the world, the information on the retina according to the direct perception ecologist group. It's the features that we see. It's basically what it is that's coming in from the outside world that allows us to recognize that there's something there. Right, but we're not just dealing with bottom-up information. We're also dealing with our own expectations, our own experiences, and we call that top-down processing. And there's a lot of top-down processing that we do. We have information from our own experience. We have the familiarity of the things that we interact with, the context in which we tend to interact with objects, and our own expectations. And those play an incredible role in object recognition and perception. Here, for example, we see an image that most of us are going to recognize as Abraham Lincoln. Why? Are there features of Lincoln that are in this image? No. Right, but it just sort of activates this famous portrait that we associate with Lincoln. If we've never seen it before, we're not going to recognize this as Lincoln. But again, there's nothing featural based that's really driving that perception. It's based on our experience, our familiarity with an image that looks vaguely like this. We can also look at a particular stimulus, and it may be ambiguous if we don't have a context. What is this? It could be a number of different things. But if we provide a context, we can easily recognize it as an H or an A, even when there are other H's or A's that are present that don't look exactly the same. Context provides a vehicle for our perception. It's a very powerful mechanism for us to be able to impose order on things that we're looking at, especially things that may be ambiguous. We expect to see things in certain ways. So if I show you this image, you may not notice at first that there's a couch floating in the air. And that's just simply because we're not usually used to seeing couches free floating in cityscapes. Right? Now, the funny thing about these kinds of context violations is that at the same time, they're both easier to see and they stand out more. It really just depends on how fast you present them to people. Right, but again, context, whether we expect to see something or not, influences the way that we process a scene. If we look at a picture of something that's been broken up in a very unusual way, like this kitchen scene, it's harder for us to identify the individual pieces because we're interfering with the coherency with which we're normally looking with that picture. Right, so here it's a lot easier to see the individual components of the kitchen scene compared to that scrambled version, even though featurally they are the same thing. Another really good example of top-down influences is what we call the word superiority effect. And in that effect, we are better able to recognize letters when they occur in the context of words that we're familiar with, like the man, compared to a non-word situation where they're just putting them together as I'm net. Right, so we like things presented in the ways in which we are used to seeing them. And when those violations happen, we can still process for meaning, but it may take us a little bit longer. Another good example of how top-down processes work is proofreading. So we may be able to read our own work, but it may be harder to notice our own mistakes because we know it's supposed to be there. We have a framework for what we're trying to say, whether that's what we're saying or not. So proofreading someone else's work is always easier rather than proofreading your own, because you don't have the same kind of expectancy effects to contend with. Switching gears a little bit, I want to talk about some lower order visual problems that influence our ability to perceive. And one interesting one is what's called achromatopsia, or cortical color blindness. Most of the color blindness that we tend to deal with has to do with the pigment level of the eye, but you can have actual brain issues that are influencing your color. And again, we're talking about the eye and photoreceptors and pigment sensitivity. That's the whole issue of 8% of the male population has a genetic issue that interferes with that type of color perception. All right, but here we're talking about something different in terms of achromatopsia. In this situation, we usually have some residual color ability, but an inability to perceive subtle differences. And usually there are other visual problems that go along with it as well, other than just color. And that's because color-sensitive neurons in the brain are also orientation sensitive. And we sometimes see some slight problems in form perception. It's associated with damage from stroke. And the injury from stroke often affects multiple visual areas, not just the color-sensitive area, which is area V4 of the cortex. Another interesting issue that we sometimes see is akinetopsia, or motion blindness. And people with this problem see the world as snapshots. They're incredibly bad at judging the direction and speed of moving objects, so they have no real sense of continuity of motion from one scene to another. And this is very specifically associated with bilateral lesions of temporoparietal cortex. Now, this does not result from only one-sided lesion. It has to be a bilateral. And the reason is that we have very large receptive fields that can be activated by information from either side. So just left damage or just right damage is not going to do it. It has to be bilateral damage on both sides. Another very interesting visual issue that's sometimes been reported in the literature is depth blindness, where people report experiencing the world as appearing flat. And there is some anecdotal studies for depth blindness, but there's really not a lot of clear dissociation between depth perception and other visual impairments. It's actually pretty hard to wipe out depth perception because we have so many cues like binocular disparity and the motion that you get when the retinal images change more for closer than further objects. Right, so it's really hard to wipe out depth. And there is no such thing ultimately as true form blindness. We have multiple pathways and sources of information about form, so we don't see things like disembodied colors unless maybe you eat some really bad mushrooms or something, which even then really we're just not experiencing what we would think of as true form blindness. Now, there are some higher order visual problems that we've already discussed with the idea of like agnosia, but I want to go agnosia or agnosia. I want to go into a little bit more detail about some things. So blind sight, we remember, it's damage to the primary visual cortex, where we have some residual ability because of the projections from optic nerve that go to superior colliculus that are part of that localization rather than identification system. If we kind of dig a little deeper in terms of what's going on with different kinds of visual agnosias, we come up with some interesting dissociations. An apperceptive agnosia is a problem in perceptual processing that's usually subtle. Patients may be able to discriminate shapes, but they'll have trouble recognizing photographs or drawings. There are severe problems with dealing with degraded images, and it's more apparent after right hemisphere parietal lesions. And the problem is worse when you show the objects from atypical viewpoints. And this shows that it's not really a knowledge-based problem. Shape matching is something that apperceptive agnosias have a really hard time with. Copying is something that they have a really hard time with. And again, they have problems recognizing things from unusual viewpoints. Associative agnosics have normal perception, but they cannot associate perception with recognition. Alright, sometimes in this situation you have people with alexia who cannot read, and that's associated with damage to posterior temporal cortex near the occipital lobe. These patients may also show difficulty describing the functions of objects, and they may show some odd dissociations. Generally, they tend to have worse recognition for living versus non-living things. And we talked about this a little bit before. Living things may share more features in common, maybe less distinct. We act on them in different ways. We may have more elaborate representation for non-living objects because we manipulate them in very particular ways. So with associative agnosia, they can copy, but they're not going to be able to recognize very well, and we may see some category-specific kinds of problems from living versus non-living kinds of objects. They're also going to have a hard time in these matching to function tests where you have to decide which of the two objects at the top has the same function as the lower object. They're going to really be distracted by the visual characteristics and not really pick up on the functional thing that they should be paying attention to. Another very interesting higher order visual problem is prosopagnosia, a problem that's specific to recognizing faces. This is most common in bilateral occipital lesions, and it's not related to familiarity, so it's not as though you would recognize your spouse or your mother or someone famous and not the face of someone you've never seen. Familiarity doesn't have anything to do with it. And interestingly, though, it is very specifically associated with human faces. So there was a prosopagnosic farmer in Scotland that was studied who could still distinguish his sheep based on their faces, even though he couldn't recognize people based on their faces. And I'm including a couple of really interesting excerpts from Oliver Sacks's famous book, The Man Who Mistook His Wife for a Hat, where he talks about meeting a patient with prosopagnosia, and he says, instead of gazing at me, taking me in the normal way, he made sudden strange fixations on my nose, on my right ear, down to my chin, up to my right eye, as if noting these individual features but not seeing my whole face. He reached out his hand, took hold of his wife's head, tried to lift it off to put it on, and his wife looked as if she was used to such things. Now, just to kind of wrap up a little bit about recognition and other modalities, we're going to talk mostly about vision because we as humans are visually dominant animals. But hearing is something that, of course, we can use in recognition. Hearing varies in terms of its sensitivity across animal species, so you can see that there's a range of sounds that humans can hear that's going to overlap some of other animals. This is the same kind of finding that we think of in terms of the light spectrum as well. Right? Sensitivity varies across species. To recognize a specific sound, the auditory system has to group together frequencies unique to a particular source. Otherwise, we hear a variety of sounds as one. And we're pretty good at separating the sources because the intensities of sources' component frequencies tend to wax and wane together because of harmonic radiations among the frequencies. Right? This is similar to the way that all animals also hear. We can locate objects based on the intensity of sound and the interaural time differences between the time of an arrival of a sound at our two ears. That varies with the location of a sound source relative to the head. Just like we can have problems recognizing things auditorially, visually, in terms of visual agnosia, we can have auditory agnosia, in which we may be able to discriminate tones in speech, but not the melodies of songs. We may not be able to identify environmental noise. And we may have very specific problems with word deafness, where we have difficulty recognizing speech. Another important aspect of recognition is that we can kind of combine these things together in terms of the information that we're getting from various senses in recognition. We have multimodal perception. We can recognize things according to touch, and we can know that something should feel a certain way based on the way that it looks. This is a particular study done by Meltzoff and Borton that some of you may remember from developmental, where they introduced these pacifiers into babies' mouths, and they wanted to look to see if the babies showed any kind of looking time difference in the way the pacifier looked relative to the way that it felt in their mouth. And what they discovered is that very young children knew that when they had this nubby pacifier in the left in their mouth, that it should look like the one on the left. Right, so we see some very strong connections between our senses and our ability to recognize. These things tend to work together, and that's why if you have a kind of agnosia in one sense, you can usually compensate fairly well with another one. We can also sometimes use senses in ways that we're not used to if we have to. So in terms of smell, we're not really used to using smell as a means of recognizing whether we're male or female, but we could, as was shown in this study by Doty, have people breathe into devices and then smell the breath of somebody else and recognize a male or a female based on the breath odor. We can do that, and we're actually pretty accurate, even though that's not normally the way that we would go about doing that kind of recognition. Taste recognition is the final thing that I want to mention. There's been a lot of research looking at the fact that we can have combinations of sour, sweet, salty, and bitter taste buds working together to define any kind of taste that we can experience, which turns out to be a little bit simplistic. We have other kinds of receptors that are present, like umami, which was identified by Japanese researchers and is responsive to the chemical MSG. Also, the idea that we have these receptors located in very specific areas of the tongue has been disproved a bit. It's a little more complicated than that. All right, but certainly taste also plays a role in our perception and is actually highly integrated with smell. So a lot of what we think of as taste is actually smell. All right, I think I pretty much covered the main stuff that I wanted to go through. Be sure you read your book really carefully. We're going to have our exam. If you have any questions, I should be available by email. I hope to be back with you on Tuesday, depending on kind of what happens with my hospitalization. I miss you all very much. I hope that this is not too jarring going through this material, in this animated PowerPoint way. Hopefully, it just kind of helps you to follow along a little bit. And again, good luck on the test. Let me know if you have any questions, and I hope to see you all next week. All right, goodbye.